Hello, everyone. Welcome back to Hidden in the Stars. On this episode of Mysteries, Myths, and Misconceptions, we're covering the confusion between the two G's commonly used in astronomical equations. There are two main G's astronomers use as variables when doing calculations: lowercase g and capital G. Both have to do with gravity. Gravity is an attractive force. It is defined by Oxford as the force that attracts a body towards the center of the Earth or towards any other physical body having mass. The one most people are familiar with, and usually fairly comfortable using, is lowercase g. This stands for acceleration due to gravity. Lowercase g is a term of specifically acceleration. It's not a speed nor a velocity. This is noticeable when looking at the units of the value, which are most often measured in meters per second squared. Don't forget the squared. This is what indicates that it's acceleration. Velocity is most often measured simply in meters per second. There is no second unit of meters to multiply the equation, therefore it is not squared. Here's a hint. When looking at measuring motion, speed equals distance divided by time, which progresses to velocity equals displacement over change in time, displacement being the difference from the endpoint minus the start point, which finally progresses to acceleration equals change in velocity over change in time. I like to think of these sort of progressions like Pokemon evolutions, with speed being the first evolution, velocity the second, and acceleration being the final evolution. There's a couple sets of astrophysics equations that can be thought of this way, whatever helps you to remember. Oh yeah, when you see these equations, you'll most likely see a little triangle in front of the variables. For those of you unfamiliar with this fun little fella, it's in Greek and its name is delta. It stands for the change in. For example, earlier when I said the formula for acceleration is acceleration equals change in velocity over change in time, it would be written as lowercase a because lowercase a is acceleration and capital A stands for area, equals delta v divided by delta t. Astronomy and astrophysics in general can get very confusing when it comes to variables. Lowercase t could be temperature as well as time, and lowercase v could be velocity, whether that be relative velocity or some other form of velocity like average or radial. It could even be types of visual magnitudes or spectral features. I've even seen v as the Greek letter nu represent frequency of photons. These are just some examples. So now that we have a little background, what actually is lowercase g? Well, it's 10 meters per second squared. Just ask any physicist. And with that, I'll show you right to the door. With not just a background in astronomy, but an original love for math, I'd like to take the next few seconds to officially let every physicist out there know that their rounding will melt the polar ice caps, create never-ending deforestation, and revert all the hard work the ozone layer has done to heal itself with that nasty hole we put in it. Your rounding is the reason we still don't know how the pyramids were built or where Atlantis went. The true value of lowercase g is 9.81 meters per second squared on Earth's surface. Wow, would you look at that difference of 0.19 meters per second squared? That may seem pretty insignificant, but if I was building a rocket, I think I might want to take it into consideration. So, for the love of all things spacey, please don't use 10. Now, here's where it gets tricky. Notice I said on Earth's surface. Gravity is not the same everywhere. Our moon's surface has about 1/6 of our gravity, making it so astronauts are seemingly much lighter and can bounce much higher. But do they weigh less? Yes. Well, you have the same amount of mass, you would weigh less on the moon's surface than on the Earth's surface. Say you weigh 150 pounds on Earth, you'd weigh around 25 pounds on the moon. But you'd still be you. Just because you went to the moon doesn't mean you'd all of a sudden fit into a size 0. Your mass remains the same. It's the force of acceleration of gravity that changes your weight. In our solar system, Jupiter has the strongest gravity at approximately 2.4 times stronger than the Earth's. This means if you weighed roughly 100 pounds at Earth's surface, you would weigh about 240 pounds on Jupiter's surface. The gravity there is crushing. One last tricky topic with lowercase g, then we'll move on to whatever the heck capital G might be. Is it positive or negative? Well, what direction are you talking about? Gravity is a force, and forces are vector quantities. Vectors have both magnitude and direction. We know the magnitude, or the strength, is 9.81 meters per second squared. Next, it's very important to specify the direction in which you want to measure the acceleration due to gravity. If you're using it to, say, measure weight, and the force is pointing towards the center of the Earth from the atmosphere, it's positive. If it's pointing from the Earth skyward, don't forget that negative sign. It seems backward, doesn't it? I find gravity to be very confusing and frustrating. If that's off-putting, have you ever heard of the experiments Galileo did with the Leaning Tower of Pisa? Look it up. I bet it twists your mind for a moment. Okay, now that's all covered, let's talk about capital G. Capital G represents Newton's gravitational constant. It's defined as a physical constant that determines the strength of the gravitational force between two objects that have mass. It appears as the proportionality constant that is used in Newton's law of gravitation. Notice how it says that these two objects must have mass. Why do we know that it's seemingly massless in space? Photons and gluons, right? So do photons and gluons have gravity? Photons are affected by gravity even though they're massless. This is described in general relativity due to gravity having to do with energy and momentum, not just mass. However, gluons are barely affected by gravity because their interactions with the strong nuclear force are so dominant. There's still some research being done on the interactions with gluon and gravity, and it's a bit of a debate as to how strong the interactions are. Let's get back to capital G's value. We know what it is, a proportionality constant. So what's it worth? 10 again? Please, just no. The gravitational constant is defined as approximately 6.674 times 10 to the negative 11 Newton meters squared per kilogram squared. There is a relationship between the two g's, and it's easier to see if you actually plug in the variables g and capital G. The acceleration due to gravity, lowercase g, is equal to the quantity of the gravitational constant, capital G, times the mass of the celestial body, closed quantity, divided by the square of the radius of the celestial body. If you then plug in the units, you can sort of see how it works a little better. The gravitational constant is necessary for understanding interactions between celestial bodies, like smaller things such as planets and stars, to even larger things like solar systems and whole galaxies. It's not a field strength like the acceleration due to gravity as represented by the lowercase g. As you can hopefully see now, the two are very different. One is describing a force between two objects with mass, and the other is a rate at which objects accelerate towards a massive body, in our case of 9.81 meters per second squared, like Earth, due to gravity. Remember, lowercase g is equal to 9.81 meters per second squared, not 10. Capital G is equal to 6.674 times 10 to the negative 11 Newton meters squared per kilogram squared. Lowercase g is acceleration due to gravity. Capital G is the gravitational constant, a proportionality constant. One relates the driving force of an object towards the center of a large body. The other relates the gravitational force between two large objects with mass. They're used in different scenarios and equations. Don't forget to see if lowercase g is positive or negative. Read the units of the scenario or equation if you can't figure out which one to use. Units will save you. Fun fact, did you know you can solve whole equations just looking at the units alone? You don't need any variables or constants, just the units. Not every equation though, just some. But if you solve them correctly, units will cancel out until there's just one left, or sometimes none. Every tough case can be solved by collecting clues. Follow the units like Scooby follows a good clue. It might just help you solve the mystery. Thanks for tuning in to this week's very long and complicated episode of Mysteries, Myths, and Misconceptions. Hopefully we were able to help distinguish between those pesky G's. We appreciate all the positive comments and feedback we've been receiving, and do apologize for not being able to respond to everyone. If you have a suggestion, we'll try to get to it as soon as possible. Thank you so much to our wonderful viewers for supporting our channel so that we can continue to upload videos. Come along and join us on our journey through the cosmos. Catch you next time on Hidden in the Stars.